Okay, chemical equilibrium. There's a reason for doing the kinetics first, even though historically chemical equilibrium was more fully understood and quantified before kinetics. It had to do with advancements in the science, in the way we treat data, in measurements. But it's easier to understand equilibrium when you have a grasp of kinetics because of the way equilibrium is not just defined, but the way it happens. So what do we mean by equilibrium? We mean a steady state. Nothing is appearing to change. In chemical equilibrium, we're looking at a reaction, right, that has reactants and products, and the concentrations of these two at some point arrive at an equilibrium position where their concentrations stay the same. They don't change. But what we understand from further investigations into kinetics is that the reaction can go both directions. So if it can go both directions, and we proved this in the lab, is that we have reactants to products going one way, products to reactants going the other way, and they can happen at different rates. I mean, they can go faster one direction than the other, but once they reach equilibrium, then the conversion from reactants to products equals the same rate as products to reactants. And that establishes the equilibrium. And what we see from the outside is no change. All right. This is what it looks like when we first start the reaction for this Haber process. We have a certain amount of nitrogen, a certain amount of hydrogen listed as the blue and the green lines. And then the ammonia is at 0 when we start. So as the reaction proceeds, we use up some hydrogen and nitrogen and produce some ammonia. And at some point, the concentrations level off and are constant. And these are stoichiometric relationships. In other words, moles of compounds and reactants and products. The other way to look at it is, well, let's do this first. Well, I've already mentioned that. We study kinetics first because we're talking about equality of rates. We can look at it this way also in terms of the red line, which would be the forward rate. And the forward rate starts out very high. Reverse rate is nothing because there's nothing over here to go backwards. But eventually, you have enough products so that you get a return rate. And those two rates, forward and reverse, are equal. Okay, so in this sample reaction, where we have water plus carbon monoxide yields hydrogen plus carbon dioxide, the question is, what do you think would happen if this reaction were at equilibrium? It's got some water and carbon monoxide still, and it's produced some hydrogen and carbon dioxide, but the concentrations appear to be static. Then what would happen if we added some water to the flask? What do you think would happen? It's not a trick question. If you increase the number of water molecules on the reactant side, then the opportunity for more impacts, more reactions to occur is obvious, right? So what would happen? The forward rate would increase until you produced enough products so that the reverse reaction comes into balance and you reestablish equilibrium. So we get a shift to the right in terms of concentration if you add more water. What if instead of that, we say you add more hydrogen? We would expect the opposite to happen. Shift to the left. We add more hydrogen, more possibilities for hydrogen and carbon dioxide to react and produce water and carbon monoxide. And there would be an imbalance in the beginning. And eventually you would produce enough reactants so that we reestablish the forward and the reverse rates being equal. All right. The conditions for equilibrium can be expressed in a formula. And before I put theirs up there, I'm going to write one up. Say we have two reactants, and their coefficients are little a and little b. And we expect products to be, oops, doesn't make any sense. There. Products to be C and D. We can express the equilibrium. Once it reaches equilibrium, we have some A, some B, some C, and some D. And we can express this concentration in terms, usually in molarity. We can also say that this expression is constant as long as the temperature remains constant. And we use square brackets to represent molarity. So the equilibrium concentration of C raised to its coefficient power times D to its coefficient power in the numerator. And then in the denominator, we have values for concentration of A and concentration of B. And that expression is called the law of mass action. The history of this was that a Norwegian chemist and his brother-in-law got together and were working on this problem, and they discovered this relationship. Now, I'm not sure why they picked products for the numerator and reactants for the denominator, but it works. You could probably do it the other way. But they established it, they investigated it, so I guess they have the right to put them in any order they want. But this is in 1864. Right? That was on the other side of the ocean. At that time, we were killing each other in the Civil War. Now they had different terminology than we do now. Description of the affinities that drive chemical reactions. That's an archaic term. But what this expresses is at equilibrium, that concentration in this relationship is constant or constant temperature. Now, the concentrations themselves can be different, right? For one set of circumstances, you could have, say, high-low, and then for another set of circumstances, you could have not so high and not so low, or not so high and even lower. The ratio is the important calculation. I'll talk about that a little more in a minute. They called it chemical dynamics, which just means in physics, if you ever take physics course, the first thing you start with after you learn the terminology and the language is you study statics. And statics just means that nothing's moving. It's like defining a simple machine, like a lever, right? So we say we've got a fulcrum and we've got a lever arm here. And if we put a force there, what force over here will balance it? And the balance means that nothing's really moving. That's statics. Dynamics implies motion. So they were studying the way chemical equations move to reach a static position. And since their investigations involve solution chemistry, they express these relationships in terms of concentration, like moles per liter. Later, we're going to learn that you can also, if all of the reactants are gases, then you can express it in terms of partial pressure, and it works just fine. As long as you are expressing, if the terms you use express concentration in some form, then this law of mass action works. So there it is with the defined terms. I will say this, because we have molarity, 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 and molarity. Since we have powers here, then the units of measure can be anything. They can just be completely outrageous, especially if you have more reactants or more products to string out here. So by convention, we don't use units. We don't even express the units. So we have to be careful when we give an equilibrium constant, we have to know what reaction it references. Yes, we have to be very particular about that. And about our calculations. If we do our calculations correctly, then if we have this K value and you have 3 of those, then we can calculate for the 4th one. And it should be in molarity if we are very careful. Okay. There are situations where we may have to, like Hess's law, we may have to combine equations to give an expression for some target equation. And when we do that, we need to know how to treat the individual K's for the components. Say we have 3 equations we're going to combine. Each one has a K. How do we combine those 3 K's to give us the final K? And suppose we have to, say, invert the equation or multiply by a constant. What effect does that have on the K before we combine them? Okay, so that's what this slide is about. If we have to flip the equation, then we simply flip this expression. And the K for that one then is the inverse. We just put these on top and these on bottom because now they've changed positions. The products are reactants and the reactants are products now if we invert the equation. If we have to multiply the equation times some factor, let's say n, in order to make it compatible and then we're able to add equations together, then this n is transferred through the entire equation to be NA, NB, NC, and ND. So we put an n there, and an n there, and an n there, and an n there. Okay? So we can factor that n out so that instead of individually n's, now that n is out here. Okay? Okay? So that means the new equilibrium constant is just the old one to that power. If we multiply it by this n, then the new K is to the power of n. And again, units are, K's are written without units. Okay. So what happens? Let's see. Do I have a slide on this one? No, I don't. if we have to add equations together, and say we have a K1, a K2, and a K3, or three different reactions, and we don't have to do anything to them, right? Let's keep it simple. Then the final K, the overall K, is equal to K1 times K2 times K3. So we multiply the Ks. All right. Okay. Regardless of the amount of starting materials, once equilibrium is established, then the K is always the same if the temperature is constant. If we change the temperature, then we've got a different K. And it's not unusual for an equilibrium K to be 10 to the minus 3 at low temperature and 10 to the plus 14 at high temperature. It can vary that much. Okay. Or it could go the other direction. It just depends on the reaction. Another point to make with this in this slide is that there's a difference between the equilibrium constant and the equilibrium position. For constant temperature, this is always a constant value. That's equal to K. The equilibrium position refers to the actual concentrations. So if we start off with a large concentration of reactants, we'll end up with a different concentration for products than if we start out with a low concentration of reactants to products. Different positions. Or if we have a reaction at equilibrium and we disturb it by adding something on one side or the other, then that will shift concentrations also. You won't have the same equilibrium position or same concentrations after the equilibrium is reestablished, but you will have that constant K with a constant temperature. So there's a difference between equilibrium constant and equilibrium position. All right, these K values have subscripts. Some of them are reserved for various expressions. And when we see that subscript, we know it refers to a certain type of reaction. In general, we would just write KEQ because there are lots of Ks in chemistry. KEQ, KEQs is to avoid confusion. If we're talking about pure water, right? And we haven't got to that yet, but when we talk about acids and bases, pure water can react with itself. Okay? Set up an equilibrium where it transfers a proton to one side, leaves a hydroxyl behind, and that hydronium. So this has a K value. It's actually equal to 10 to the minus 14. And that, when you see KW, it always refers to that reaction. Okay. Ka. Ka refers to acid ionization. So if we have HCl and produces these products, then their concentrations go into this expression. And when we say K sub A, we always mean acid ionization constant. They say dissociation. It's proper to say ionization rather than dissociation. Let's see, another one, solubility product. We'll get to that one later on too. KSP stands for solubility product. And I'm not going to go into details for that yet. And then KF is referred for a formation constant for complex species. And we'll actually do a lab on that one. Well, yeah, we'll do a formation constant lab. And then if our values for this KEQ, well, we generally think of this in terms of molarity for that one. If we use this one, K sub P, we're talking about partial pressures. Right? So the pressure of not little a, pressure of A, or pressure of B or C or D. When K sub P, we're talking about partial pressures that express concentration. Okay, so here's what it would look like if we take the Haber process. Fritz Haber took nitrogen gas, hydrogen gas, made ammonia. He was a good loyal German in the late 19th century and the early 20th century, and he wanted to help his country. We were embargoing. The world was embargoing Germany for its aggressive stance, embargoing guano from primarily Chile, the coast of Chile. We had hundreds of feet deep. Birds have been pooping there for hundreds of years, and it just piled up. And this was a source of nitrates. And nitrates are essential for explosives, making explosives, or gunpowder, or whatever they needed. At this time, they might have had access to nitrocellulose or gun cotton. But they needed nitrates. So if he could get nitrogen from the air and fix it as ammonia, then the reaction from ammonia to nitrates was very simple. This was the bottleneck. And he figured that one out, how to do it. And Germany had all the explosives it could handle. All it needed was energy. So if we express this in terms of molarity, then we have that K on the right. Ammonia to the second power, nitrogen to the first, and hydrogen to the third power. If we express it in terms of partial pressure, because all of those values are gases, then we can use partial pressure. And P sub ammonia to the same powers as in the other expression. I may have a slide on this, but I'm going to say it now. When we write the expression for K, we don't include solids or pure liquids. Right? We only include gases or solutions of some kind. It doesn't have to be aqueous, but as long as it's a solution, then we include these. So the expression never includes solids or liquids. If solid or liquid is part of the formula, the chemical reaction, then you leave it out, because these concentrations don't change. We only want the ones that change. All right. So if we have equilibrium, partial pressures are given as these values for this reaction, then we just simply plug them in and we get a value of 3.9 times 10 to the fourth. Right? So what does that actually mean? I probably got a slide on this also, but I'm going to talk about it now. What that means is that very large value, 10 to the fourth, because of the way the K is constructed, means that we have lots of product. The numerator is huge, as opposed to the denominator, which is small. That means that at this given temperature, under these conditions, the K is very large and favors products. Now, if we calculate if our data allows us to calculate the K in terms of molarity, then we can convert that to K in terms of partial pressure using this formula. Right? So the K using partial pressures is actually equal to the K EQ in molarity terms, with R as our gas constant. Temperature, of course, would have to be in Kelvin. And then this one is the one that throws most students, delta N. In order to calculate delta N, you need a balanced equation. And you have to take the sum of the coefficients of the gaseous products minus the gaseous reactants. So in this case, where we had nitrogen and hydrogen yields ammonia, that would be 2 here and 3 there. Then the delta N for this one would be 2 minus 1 plus 3, or minus 2. So that would go right in there, minus 2. The R is our liter atmospheres per mole K, or at 0.08206 would be that R. And then we could go one direction or the other. At this given temperature for this reaction, if we know this value, we can calculate that one. If we know this one, we can use that as our unknown and solve for that one. It goes both ways. So the other lesson that this tells me is the K EQ is not going to be the same as the KP. Okay, so in this case, let's say we have that value KP that we calculated earlier, and we put that KP in here, 3.9 times 10 to the 4th. We leave this one as our unknown. We plug in this value as a constant, and we have to know the temperature. So at 35 degrees C, that is 35 plus 273 is 308 for the temperature. And then this one is minus 2. And we calculate the this K value as 2.5 times 10 to the 7th, which again says the reaction is favor the products. Now, because, and it should be obvious actually, we've got units of, for this one, we got units of atmospheres here, here, and here. And for this one, we have molarity here, here, and here. So they can't be the same number. Okay. We can speak of, we've done this a lot, homogeneous versus heterogeneous. A homogeneous equilibrium is where all the reactants and products are in exactly the same phase. You could have all gases, like this reaction, or you could have everything in aqueous solution. That's a homogeneous equilibrium. A heterogeneous equilibrium is one in which we have solids or liquids imposed. In the top one, we have gas, and we have a solid and a solid. In the bottom one, we have a liquid and a gas and a gas. So those are heterogeneous equilibrium. And the heterogeneous equilibrium are the ones where we leave values out, because we're not going to have a concentration value for a solid or a liquid. If it's a pure liquid, it's constant. All right. Well, okay, here's the slide I was making a point with. Pure solids and pure liquids and solids are not included. So with this particular reaction where we have potassium chlorate decomposes into potassium chloride plus oxygen, the only value in that expression is oxygen. we used to take solutions of that potassium chlorate, the concentrated solutions, and dribble it on the floor. And when it dries, it produces a little white powder that it's hard to see on tile floors. So somebody come walking in and they step on it, and it's just enough energy to make it decompose into potassium chloride and oxygen and produce that gas, and it goes pow wherever you step. Okay, so this slide is just in black and white and blue. What I was explaining earlier. What does that K mean? If it's much, much larger than one, we're favoring products. If it's much less than one, we're favoring reactants at that given temperature. If it's very, very large, if it's extremely large, then the reaction essentially goes to completion, and we have almost nothing left of reactants. Oh, by the way, when we disturb a chemical reaction that's at equilibrium and it shifts, right? If you say it shifts to the right or the left, you have to reference a balanced equation. If you answer a question without that balanced equation there and you say left or right, nobody knows what you're talking about. Okay. Or you could say it shifts toward oxygen, or shifts toward potassium chloride, or it shifts toward potassium chlorate. Then they know what you're talking about. And here again, if the I've already done that one. If the value is extremely small, much, much less than one, then the reaction there's an insignificant amount progressing toward products. Now, your textbook might say, if the equilibrium constant is 1, then you have equal amounts on either side. Can't be, because of the coefficients. But if we say much larger than 1 or much less than 1, then we're safe. Okay, if the equilibrium lies to the right, the value of K is large, greater than 1. And if it lies to the left, it's small, less than 1. Now, suppose now up to now, I've been implying that we put reactants together and there are no products. We let it go to equilibrium. But sometimes we have reactants and products together and we mix them together, and we want to know which way the reaction shifts to make its equilibrium. That's where this concept of the reaction quotient comes in, the Q value. And the Q value is expressed in the same way as the equilibrium constant, only we don't use equilibrium values. So I would use, in that case, I would just use parentheses instead of square brackets. And then this would be, this would be C and D using our generic equation. And this would be actual concentrations before equilibrium. Okay? And that'll give you a value. If we're trying to determine which way it will go, left or right, for an equation written as A plus B equals C plus D, then we can compare this Q to the K for that expression at any given temperature. Right? So the K will be a certain value, right? Whatever that is. And we can compare this one to that one to see which way it should move. Right? The easy one is, if Q happens to be the same as K, we know it's not moving. We've established equilibrium right at the beginning. If the Q is greater than K, what does that mean? That means that we've got too much product. If Q is bigger than K, we've got too much product and we shift to the left, right? And vice versa. If Q is less than K, that means we don't have enough product, and we shift to the right. Okay. Now, this is going to be an important concept, an important skill when we actually try to determine equilibrium concentrations for any given reaction, because we have to know which way it's going to go toward products or toward reactants with the given concentrations in order to complete the calculations. And we'll work some examples. So here we have the iron 3 plus ion is reacting with the thiocyanate ion to produce iron 3 thiocyanate. This is and everything's in aqueous solution. What we're actually producing here is a complex ion. It remains in solution. So if we're given at equilibrium 6 molar iron 3 plus and 10 molar thiocyanate are mixed at a certain temperature, and at equilibrium the concentration of the complex ion is 4. What is the value for the equilibrium constant for this reaction? Okay, so we're given initial concentrations of the iron 3 plus and the thiocyanate, and then we're given final concentration for the complex ion. So those are two different situations. The first concentrations are non-equilibrium. The last one is equilibrium. So how do we approach this problem? All right, here's the way we do it. We identify our values, and then we set up a table. It's called an ICE table. The way I set these up is I like to write the reaction up here and spread it out a little bit so I have room to write my numbers in. This is in equilibrium with FeS2 plus. Notice that when we combine 1 minus and 3 pluses, we get 2 pluses. Okay, so we balanced our charges. Okay, so we have this initial conditions, and then how does it change, and what does that give us in terms of equilibrium? That's what the ICE means. Okay, we know that our initial concentration is 6 and 10 molar, these two. 6 and 10 molar for these two. And this one's 0. Okay, now initial conditions. We're told that a measurement was made of this ion and found to be 4 molar at equilibrium. Right? So that's where that one goes. Now, from here on, we have to logically input the rest of the data. How did this one get there? It had to change in such a way that we added 4 molar for the change. That's how it got there. Okay, so where did this come from? It came from here. The coefficients are 1 to 1 to 1. So if that one's a +4, this one has to be a -4. And that's the only place it could come from. And it also had to come from this one. So that gives us at equilibrium, we have this molarity left for the iron and this molarity left for, now we have equilibrium values, we can calculate the K. And that's what the slide is telling us. This calculation, let's see, there's more to that answer. There it is 0.333. So the K at this temperature is 0.333. As long as we keep the temperature the same, then this value allows us to do more deductive calculations for this reaction. Like if we're given this and this and this, we're given a different value here and a different value here, different equilibrium position is established. Then we can fill in these parts because we know that value. Now, we may have to use unknowns in the beginning, like let that concentration equal X. But it can be solved. Okay. So in this case, we're starting off with a different initial concentration, 10 molar iron and 5-cyanate ion starts off at 8. Okay? So we're going to have a different equilibrium position. And at the same temperature, and this is 0 still. Okay, so now we have different values here. Okay, so first thing we have to decide is which way is this reaction going? We don't have to calculate Q because that was 0. We know it's going that way. Okay, so it's going to produce. What's the question? Equilibrium concentration of that value. Okay, so if we want to know this value, then how did he get there? Well, we had to add that much, didn't we? Okay, that means we had to subtract this much and subtract this much. So at equilibrium, we have 10 minus X and 8 minus X. So now we have an expression, A equals 0.333 equal to X in the numerator divided by 10 minus X times 8 minus X. Okay? And we can solve for X. Let's see, let me flip the slide so we can get more of this in here. Come on. There we go. All right. Here's the problem that we often encounter in this ICE technique. Quadratic equations. Right? If you expand this to the polynomial, you're going to get X squared and X and a constant value. So I've worked it out here, and if we have to use a quadratic, there's a simple formula for that. Right? In fact, I don't trust myself to remember it, so I pasted it to the back of my calculator. If we set it up so that what we want is X equals, or X equals the equation such that you have to have this. You have to have AX squared plus BX plus C equals 0 in order to use the quadratic. So we would have to solve this equation so that it's in this format. Then we can say that X equals minus B, or the coefficient of this X, plus or minus the square root of B squared minus 4AC all over 2A. Okay, that's the solution to the quadratic. Now, you could get something a lot more complicated. You could get a cubic equation, and there is a solution for the cubic, but you take this one and go like that. But we don't do that. There's another method that we're going to use. It's called successive approximations. And in this case, we have to use the quadratic. because this value is too close to 1. If the value is very, very small, if it's a 10 to the minus 5 or 6 or 7 or something like that, then we can make an approximation and say, all right, well, it's not going to give us much product, so that X is going to be very small. So we can approximate this one to 10 and that one to 8 and leave that X for the solution. That simplifies it. Then we have a rule that we have to satisfy after that. But for now, we get this expression, and once we solve that equation and set it up in the correct order, like down at the bottom at the tail of that arrow, then we can plug those values into the quadratic. And notice we have a plus or minus. So one solution gives us 15.99 and the other solution gives us 5. Then we have to decide which one makes sense. If X is 15.99, how did it get there? That's only 10 and that's only 8. Can't happen.
Yeah.
So the other one is the only logical one. So X equals 5. Okay. This is another one with a different equilibrium position. We have 6 and 6 here. We go through the same procedure and we find that it's 3 molar now for that answer instead of 5. Okay, so this is just a way to solve equilibrium problems. And these are general instructions, right? You got to have a balanced equation to start with. Otherwise, you can't write the mass action. Then you list the initial concentrations in your ice table. And if necessary, if they're non-zero values for all of your components, reactants and products, then you have to calculate Q. But if any one of them is 0, then you know which way it's moving. If there's one of them 0 on this side or one of them 0 on the next side, it goes this way or that way. All right. Then we define the change, and this takes a little practice. Try to define your unknown such that when you solve for the unknown, you got your answer. That's not always possible, but whenever possible, pick X to be the answer that's being asked. And then substitute those values, including the unknowns, into your mass action equation and solve for that unknown. And then check yourself, right? Take that value and set up the equilibrium values for each of your reactants and products using the solution that you came up with. Those are real numbers. Put them into your equation and see, does it give you that value? That's just a check on yourself. Be sure you don't make any math errors. All right, these are sample problems. I'm not going to go through all of these. We would work them exactly the same way as before, and all the quadratic equations involved. Here's the answers for each one of them in case you want to try. Okay. Yeah, first two give us exactly the same concentration. How about that? Okay. So here we got another one. Let's see. I'll leave the quadratic up here and get rid of that one. 2 mole sample of ammonia is introduced into a 1 liter container. At a certain temperature, the ammonia partially dissociates according to this equation. So this is essentially Haber in reverse. But is that balanced? No. It's got 2 nitrogens on the left, on the right and 2 and 1 on the left. So we have to balance the equation. So balance the equation, we would get NH3, and these are all gases. So I need 2 here and 3 there. That's our balanced equation. So we put 2 moles in a 1 liter flask. So what is the initial concentration of ammonia? It's 2 molar, right? 2 moles per liter. And we have nothing here and nothing here. It's allowed to dissociate. So the change equilibrium is expressed this way. All right. At equilibrium, 1 mole of ammonia remains. So 1 mole per liter is the concentration of ammonia after equilibrium. Right? So what had to happen here? We had to lose 1 molar here to give us that. Okay. That means if we lost 1 here, only half of it is going to show up here, because this represents 2 mole. 2, this represents 1. This is plus 0.50. And this is 3 times that. Okay, molar. And that's the equilibrium concentration also, because there was nothing to start with. Okay? All right. So now we can calculate the value of K. So is it going to do it or just give me the answer? Just going to give me the answer. So let's set it up. So this K now is the inverse of the K for the Haber process, because it would be flipped. All right, so this one is the KEQ, then it's going to be this one to the first power, this one to the third power, and this one to the second power. Okay. So let's see, 1.5 cubed, 1.5, 3 and cube it, okay, 3.375 times 0.5, and divided by 1. So I get, I did this right, 1.69. There we go. That's our K value. All right. And at this temperature, what would be the K for the reverse reaction? Be the inverse of that, wouldn't it? Yeah. So the K, and we could write that as K to the -1, which means inverse. So 1.69, we take the inverse of that. That would be 0.593 for the reverse reaction at whatever that temperature is. It doesn't tell us what the temperature is. Okay. Here we got another decomposition. Dinitrogen tetroxide. Yeah, dinitrogen tetroxide. So this one goes from this, right, to 2 of these. And they're gases. And we're given the equilibrium constant, 4 times 10 to the -4. KEQ equals 4 times 10 to the -4. Okay. What's the equilibrium concentration of these two, both reactants and products, if we have 1 mole sample of N2O4 in a 10-liter vessel? So initial is 1 mole per 10 liters. Right? That's equal to 0.1 molar. Right? And then we have 0 here. So we're going to have some change, and then we find out equilibrium. So what's the change? Well, it's going to go that way. It's going to, whatever we lose here, let's see, calculate the equilibrium concentration of this one. So let's make this one minus a certain amount, x. That means we're going to have 2x on this side, right? All right, so this is going to be 0.100 minus x. And this is going to be 2x. All right, so whenever we find x, we're going to have to subtract it from 0.1 to get our answer. Okay. So we would say this value, 10 to the minus 4, equals 2x squared over 0.100 minus x. I think that's right. X squared. First power. Okay. I'm looking to see, can we simplify this any further? Right, we're going to end up with a squared value here and a single power here. This is going to be a quadratic. So this value is very small. That means we're not going to produce a whole lot of that. So I'm going to say this is close to 2x squared over 0.100 because x is a lot smaller than 0.1. And that should be easier to solve. So first thing I'm going to do is multiply this one on both sides. So that gives me 4 times 10 to the minus 5 equals 4x squared. And then I'm going to go straight to, I'm going to divide this by 4. So that's 1 times 10 to the minus 5. 1 exponent 5 here. And then square root. So I get 3.16 times 10 to the minus 3. So just stand back and observe. This is a very small value. So it was a lot less than 0.1. But to prove, let's see. Let me go through. Let's see. Here we go. Here we go. Here we go. And we should end up with 0.097. Okay, I messed up. Oh, that's not the answer. The answer is 0.100 minus 3. 1, 2, 3. 0.00316, right? Yeah. That's the answer. And 1 from 9 is 8. And let's see. Like that. No. Only need 2. This one is under here. 0. So that's 4. 1 from 9 is, wait a minute. Yeah. That's 4, 9. This is 6. And this is my mind's not working good. Zero point 0.09684. So if we round it off, no, it's not 0, 0. should be at that. Right there, there, there. That's correct. So this is the answer. 0.097. I cautioned you against doing what I did, and then I went ahead and did it myself. Yeah, there we go. Concentration of NO2 would be twice this value right here. So it'd be 2 times that value. 6.32 times 10 to the minus 3. Okay. Let me see. Am I going to introduce the rule yet? Not yet. There's a rule called the 5% rule. What if you make that approximation, then you want to take this X value and put it back into these values here. Put that X here, that X there. Stick those into your equilibrium expression and see if it gives you this number within 5% error. That's what the 5% rule is. Okay, Le Chatelier's principle. We've actually been talking about Le Chatelier's principle. We just haven't given it a name yet. It's what happens to an equilibrium, established equilibrium for a chemical reaction when you disturb it. If a change is imposed on this equilibrium system, the equilibrium position will change, will shift in order to reestablish equilibrium. It will compensate. It's almost as if it has a brain. It's going to move a certain way to reestablish equilibrium. That's Le Chatelier's principle. There are 3 recognized disturbances that we can apply to an equilibrium equation, equilibrium position to invoke the Le Chatelier's principle. One is concentration. We talked about concentration already. Right? All you have to do is add one or more components to the reactant side or the product side, or you can remove products or reactants and shift the equation also. Good example of that is the Haber process, right? These are all gases. That makes ammonia. And that's 2, and this is 3. In the reaction vessel, it would come to equilibrium. And then what Haber did, well, he did several things. But one of the things he did was, these are all in the same mixture. Right? They're all together in the reaction vessel. So you bleed off some of this reaction mixture, and you cool it. Well, the boiling points for nitrogen and hydrogen are very, very, very low. The boiling point for ammonia is a lot higher than they are. So if you cool it down just a little bit, you're going to get ammonia liquid. And then you just send what's left over, the nitrogen and the hydrogen, back into the reaction vessel. And what you've done is you remove some ammonia and you've added nitrogen and hydrogen back into the mixture, and it shifts the equilibrium to the right again. And you just keep doing that cycle. You just bleed off some of it, remove the ammonia, and send the reactants back in. That was one of the things that Haber did. The other thing was very high temperature and a catalyst. He used finely divided iron as a catalyst. We'll talk about catalysts in a minute. That's one way to shift an equilibrium, is change the concentration of any of the components. Oh, a got a video coming up. Okay, let me start this video.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay. So it's easy to understand how adding something to one side or the other shifts the equilibrium. We just increase that one or increase that one. It's a more difficult concept to follow the removal of some of these. And it's difficult to remove them. Once they're in solution, it's hard to get them out unless you couple a reaction with them. And that's what we've done here. This last one that shows we coupled mercury 2 plus with this reaction, and it produced this complex ion, which effectively removed thiocyanate ion. Let's see, that's right. Well, we would have to have two of these then. Anyway, by coupling a reaction like this, we can remove one or the other of reactants or products. And that's what we're going to do in Le Chatelier's principle a week from Thursday. A lot of the reactions in that procedure are second coupled reactions in order to get that desired shift. Okay, the next change that will shift in equilibrium is temperature. The shift of the K, now this is a rule of thumb. What K actually does is shift the production of product or the production of reactants, which changes the K. But if we have a K to start with, and we also know is the reaction endothermic or exothermic, then we can use a rule of thumb to say it's going to shift this way or that way. Okay, so if we have our generic equation, and it happens to be, let's see, the K is going to be like this. Let's write this out like that. It's going to be C, little c, and D, little d, then A, little a, and B. B. If this is an exothermic reaction, think of the heat as being evolved. In other words, it's a product. Right? Exothermic means product. So there's your enthalpy as a product term. So that would be on this side. Right? So now that we know that, what happens if we increase the temperature? Right? If we increase the temperature, then we're increasing a factor on this side of the equation, and it wants to shift to reactants. Right? So we increase this one, and we have to decrease these factors in order to retain that K and produce some of these. So we increase the T for exothermic. Exothermic reaction, increase T, we shift to reactants. Right? For an endothermic reaction, and vice versa. If we decrease the temperature, we're removing that factor and we shift it to the right. For an endothermic reaction, that term now would go on the other side. Right? It would be a term in the products. I mean, the reactants, excuse me, reactants. If we increase the temperature here, then the shift would be toward reactants. Why did I say that? That's products. Exothermic means products. And this is reactants. Okay, and vice versa. If you decrease, if you remove some of this term, it shifts back that way. Now, what actually happens is the change in temperature changes the equilibrium position for these factors, and that's not really part of the calculation. But it's easier to quickly determine the direction of the shift for equilibrium position if you look at it this way. Okay, the last factor that we're going to introduce here is pressure. So we have pressure of A times, no, sorry, pressure C times pressure of D to the little d and the little c over partial pressure of A, pressure of B, little a. So now this is if all of these are gases. If you have solids and liquids in there, you just ignore them. But if you have a gas and an aqueous, then your best bet is to go, don't use Kp, use KEQ, molarity. Okay, so how does pressure affect the equilibrium? It depends on the balance of moles of gas. So if we have a, let's see, let's use the Haber process again. Right? N2 is a gas, H2 as a gas. It's in equilibrium with ammonia. It's gas. This is 2 and this is 3. Okay. Add up the number of moles of gas on each side. So the total number of moles here is 4. Right? Total number of moles here is 2. Okay. Once we're at equilibrium, then if you change the pressure by decreasing the volume, Boyle's law, decrease the volume, what is this thing going to try to do? It's going to try to relieve that pressure. And we know that if it decreases the number of moles of gas, the pressure will go down. Right? So since we have this relationship, if we increase the pressure on this reaction vessel, then it's going to shift toward products. Okay. And that's another thing that Haber did. He increased the pressure of his reaction vessel to a couple hundred atmospheres. That promoted the movement toward product. And vice versa. If we have this reaction and we increase the volume and decrease the pressure, then we're going to get a shift to the left to make up for that pressure decrease by making more moles of gas. Okay? If, on the other hand, you have a reaction where the number of moles of gas on the reactant side is equal to the number of moles of gas on the product side in the stoichiometry, then changing the volume and changing the pressure consequently will have no effect. Right? Also, simply increasing or decreasing the pressure. Say we increase the pressure by shoving an inert gas in there. That will have no effect because we're increasing the pressure, but we're doing it with a non-reactant. Right? This doesn't involve any of, so it just stays where it is. Or we use an inert gas. Suppose you use a compound that doesn't react with any of those. It doesn't have to be inert gas. It could be anything else that's not part of the reaction, assuming it doesn't produce a side reaction. Okay, we know inert gases won't do that, so that's why we tend toward that just in the discussion. Okay, oh, that's it. In your copy, I didn't have any. I got it. Think it one time. Yeah, that's okay. at one time I had some more videos, but there was only one of them that actually explained things, and that was the temperature. Okay, so we're finished early. That's equilibrium, and we'll pick it up on Thursday with the review document. I'll pick some out, and if any of them give you trouble, bring those, and we'll talk about them.